Hello and welcome to seminar number 12. Today we are going to talk about nuclear chemistry yet again. And today's topic is nuclear reaction basics. So what is the plan for today? We are going to refresh the unit Bahn, which I talked about in the first seminar, and then the nuclear reaction equation, which is again a refresh from the first seminar. And then we can talk about neutron irradiation and light projectiles, and then some exercise for you to try if you have really understood what I said in today's seminar. So, let's get started. We will start with the unit Bahn, and a Bahn is defined as an area, which is 10 to the power of minus 24 square centimeter, and it describes how well a nuclear reaction happens. If you look at this graph here, you will have different Bahns, or Bahn. For example, we have the geometrical Bahn, so that describes how big the cross-section of the nucleus that you are trying to get a nuclear reaction with actually is. So for the uranium, we have a geometrical Bahn of 1.74. But for a different reaction, this nucleus can appear larger, and this area that it then covers, apparently, is described with another Bahn. For example, the fission Bahn. So for an incoming thermal neutron, in order to do the NF reaction, so the neutron-induced fission reaction, this uranium-235 atom doesn't actually appear to have a area of 1.74 Bahn, but it actually appears way larger with an area of 583 Bahns. The geometrical Bahn is really small for the hydrogen atom, and for the uranium nucleus, it's quite large, as you can see here. So it describes the difference between the geometrical Bahn and the Bahn for the reaction that you are looking at. It describes how big this nucleus actually is versus how it appears for this reaction. Of course, a larger area will give you a higher chance of that reaction actually happening. Okay, so now we have to describe this nuclear reaction if it happens. And when we are coming from chemistry, as it's nuclear chemistry, we have in normal chemistry a chemical equation, for example, methane burning on air, producing water and carbon dioxide. This is described by a reaction that looks something like this. And in nuclear chemistry, we have something like that. Bismuth-209 gets irradiated with thermal neutrons in order to form a bismuth-210. A nuclear reaction would look something like this, where you will have the target, the bismuth-209. Then you have your projectile, so this is the stuff that flies in. This is the neutron. You will then have an ejectile, which is in this case a gamma photon, very high prompt gamma photon. And then you have the residue, so what is left after the reaction. Hopefully the stuff that you would want. Yeah. Now classify different reactions into different types. So, for example, we have the elastic scattering and the inelastic scattering. These are very fast processes that we don't talk about. But for now, we are focusing on the exchange reaction and the capture reactions. And yeah, sometimes about fission is also quite common when it comes to nuclear chemistry. Okay, this is what it normally looks like. So you have the N-gamma reaction, so a neutron capture with neutrons of different energies for the uranium-235 atom. Yeah, we are going to talk about neutron irradiation on this slide. So here we have the neutron capture cross-section among different neutron energies for the N-gamma reaction with uranium-235. But we can also have some other reactions where the neutron is the projectile. But the most common one is the N-gamma reaction of uranium-238, which produces uranium-239. This is the plutonium production, because the uranium-239 then does beta-minus decay to form neptunium-239, which then also does beta-minus in order to then produce the plutonium-239. Yeah, there is an N-gamma reaction. But of course, we can have other reactions. For example, the exchange reaction of chlorine-35. If you irradiate that with neutrons, you will not only have an N-gamma reaction, but sometimes you will have an NP reaction. And this will then form sulfur-35, which describes the production of radiosulfur, which is quite important. I made a video about sulfur-35 and I will make some more. And you will have some exotic reactions, for example, the N2N reaction. This is the cause of natural occurring neptunium. So in the very unlikely case of neutrons in the environment that can hit a uranium-238 atom and don't do the N-gamma reaction, they can sometimes induce an N2N reaction, causing uranium-237 to be synthesized, which can then do beta-minus decay in order to, course, natural levels of neptunium-237. This is how you can look at nuclear reactions. So you have your target, and depending on projectile and ejectile, you can move across the chart of nuclides like this. Yeah, some nuclear reactions are direct nuclear reactions. The other type of nuclear reactions are compound reactions. But first, let's talk about the direct nuclear reactions. These are very fast. They are in the tens of minus 22 seconds, and they involve mostly high energy projectiles, and they happen only on the surface of the target, and the projectile only acts on a part of this target nucleus. Some examples involve the stripping reaction, where you have a DP reaction. So you have a deuteron, a proton and a neutron, deuterium ion, that gets shot onto the target, and only the neutron of this deuterium will be absorbed, leaving the proton behind, and which will then be described formally as the ejectile. But this is not a deuteron coming in and another proton coming out, but this is actually the proton of the deuteron, and this is a stripping reaction where the deuteron gets stripped of its neutron from the targeted, it irradiates. But you have the opposite, which is a pickup reaction, where you have a helium-3 alpha reaction, where you irradiate with helium-3 ions, and since they would have to pick up one neutron of the target in order to form this double magic nucleus, the alpha particle. This is a pickup reaction where the opposite happens. So the projectile strips a neutron off the target. And another type of nuclear reactions, this is the compound reaction, where you will form very short-lived compound nuclei. For example, we have the production of fluorine-18. So you have a proton coming in onto the oxygen-18 target. They will form a compound nucleus, the fluorine-19, and this compound nucleus will then eject a neutron, forming then the residue, the fluorine-18. Common reaction that I can see on the internet quite often is the production of neutrons in a neutron source. So you have the beryllium, which will be bombarded with alpha particles and will then form a compound nucleus, the carbon-13. And this carbon-13 compound nucleus will then irradiate one neutron in order to form the residue, the carbon-12. It is really important that if you look at this, so you have the beryllium-9, which gets irradiated with alphas, and then most of our students think, okay, we have the carbon-13, but this is stable, so why should it emit a neutron in order to do the alpha-N reaction? Well, this carbon-13 is in a ground state, but the compound nucleus is a very, very high energetic version of this carbon-13, so this and these are not the same, not even remotely. So you can look, I also do that. So you can move across the chart of nuclei like this, so alpha N. But of course, we don't stop here. So this is not alpha and then N. You get what I'm saying? This is how I mentally move through the chart of nuclei when looking at nuclear reactions. But you can not only irradiate with neutrons, you can irradiate with other stuff. For example, light projectiles. So this is the proton, a deuteron or alphas is the most common type of projectiles. So you can irradiate with protons, so H1 positive ions or negative ions. The same case for the deuterons, and also alpha, so helium 2+ ions. But since they are charged particles, they require acceleration, and for that we will use some very heavy machinery like the cyclotron or the Cockcroft-Walton accelerator, which look something like this. So you have your charged particle, and they will be accelerated via a magnetic field, and then will be accelerated more, and then they can leave and hit the target and irradiate that, and you can have your nuclear reactions. Okay, now we know our projectiles, our targets, and possible ejectiles in order to form the residue that one wants. Exercise. This is a very common exam question. So you will get your residue that you would want to produce and now make 3 possible nuclear reactions how you could get this residue. For example, fluorine-18. You could stop the video now, okay? And then I will give the solution, but there are many different right answers. In the exam, it's not if it's realistic, but is it possible? You could do a N-gamma reactions. For example, you can have fluorine-17 and do an N-gamma reaction in order to form this fluorine-18. Is it realistic that you have a fluorine-17 target? Of course not. But you could produce fluorine-18 via an N-gamma reaction with fluorine-17. But you can also produce it via having a D-gamma reaction or a TN reaction and so on. You can use that as a cheat sheet. But most commonly, it is, as I said on the previous slide, is produced via oxygen 18 doing a PN reaction in order to form the fluorine 18. This is a target that one could use. So this is oxygen 18 enriched water, type of heavy water. Now do the same for oxygen 15. And as I held it in the nuclear seminar on the Discord server, most common type is the N reaction. So irradiate oxygen 14 with neutrons to do the oxygen 15. This is correct. But if you do these capture reactions, if you irradiate with neutrons or protons, do not forget the gamma reaction. So this is not a P reaction. This is a P gamma reaction. This is an N gamma reaction. Do not forget that. This ejectile is really important if you're writing down nuclear equations. Otherwise, this solution will be wrong. Yeah, feel free to use all of this in order to come up with creative suggestions on how one could produce oxygen 15 with the most common light projectiles. On a large scale, it is usually made via nitrogen 14 gas, which will be bombarded with deuterons and perform a DN reaction. So deuteron is one proton, one neutron, and one neutron coming out. So this is how it's done a large scale at the cyclotron. Another very important isotope is the carbon 11. Of course, the classical N gamma reaction, P gamma reaction, of course, right? And now here comes the solution. This is also done via a target being the nitrogen 14, which will be bombarded with protons and do a P alpha reaction in order to form the carbon 11, which can then be carried out by a stream of oxygen in the form of carbon 11 carbon dioxide in a nitrogen stream. How would one produce tritium? There are two very common ways on how to produce tritium. One solution is the N-alpha reaction with lithium-6, so N-alpha reaction. This is why we have so much lithium-6 in nuclear labs, because nuclear power plants do not want lithium-6, as this can happen, and you will have tritium in your coolant water, and this will just add to the overall radioactivity, and you would have to deal with tritium. And this is why they separate out the lithium-6. This will be a waste. And the lithium-7 does not do that, so therefore there is no risk of excess tritium production. But of course, you can also produce it via an N-gamma reaction with deuterons, with deuterium, so heavy water. If you have a heavy water cooled reactor, this is stuff that could happen. Even though this reaction is very unlikely, as you can see here, this is the neutron capture cross-section in barn. So this is 0.00051 barn. This is very unlikely, as normally when we are talking about nuclear reactions, they happen if this cross-section is 1 barn or higher. So this is nowhere near 1 barn. Last exercise, how would one produce polonium-210 or astatine-11? Of course, feel free to be creative. And now here comes the solution. And the solution is that both use a target. This is the bismuth-209. Of course, this is a very old chart of nuclides. Now we know bismuth-209 is radioactive. It's not completely stable. And you either irradiate that with neutrons to form the bismuth-210, doing an N-gamma reaction. And this can then do beta-minus decay. So it was a bit of a trick question, as you produce bismuth-210 and then it decays, forming polonium-210. And in order to make the astatine-211, you irradiate that with alpha particles and do an alpha-2N reaction in order to then produce the astatine-211. This is the most common way on how to produce these two isotopes. Of course, there are other types. And with that being said, thank you for your attention and goodbye.